Great, we're still on section 12.5, and now we're just going to make shit run into each other. And we're going to start off with intersecting lines. And if you have two lines in space, right, let's just think about this for a second. If you have two lines in space, what can happen? Well, they can be parallel, right? So they can be like that. All right, cool. They can run into each other, all right? And if they run into each other, then they'll intersect at a point, or they can be skew, right? So what happens is I suck majorly at drawing, but let's just say that like there's going to be this distance from these two lines, right? That they just miss each other by. So these two lines then are skew. And remember, we're talking about 3 dimensions here. So lines can intersect, they can be parallel, or they can be skew. And so we're going to consider the case then where they intersect, and that means they're going to intersect at a point. And I kind of already covered this case already in a previous video. I think it was in the planes video. It was in the equation of planes. In the last example, I had to intersect two lines. So this will be really fast. So what happens when you intersect lines? So let's take this line. So L1 will be 3 plus 2t, or x is equal to, right? So L1 has x equals 3 plus 2t, y is equal to negative 1 plus 4t, and z is equal to 2 minus t. And then, of course, t can be, any value you really want it to be. And then L2, which is the second line, you got x is equal to 1 plus 4s, y is equal to 1 plus 2s, and z is equal to negative 3 plus 4s. And again, s is anything you want it to be. So, all right, how do we intersect these guys? Well, we just have to set the x is equal to each other, the y is equal to each other, and the z is equal to each other, right? So you got 3 plus 2t is equal to 1 minus 1 plus 4s. You got negative 1 plus 4t is equal to 1 plus 2s. And then you have 2 minus t is equal to negative 3 plus 4s, okay? And so you just want to deal with, I guess, which one you're going to think is easiest, because you need to solve the system of equations. And how are we going to do this? Well, okay, so we can do it the following way. From this first equation, I got 2t is equal to negative 2 plus 4s, right? That's by subtracting the 3 from both sides. Divide that by 2, you got t is equal to negative 1 plus 2s, right? So that's good. We can live with this. And even better, let's write it as 2s minus 1, okay? So t is equal to 2s minus 1. And then from this guy down here, I got 2 minus, well, t is 2s minus 1, right, is equal to negative 3 plus 4s. And so now I got 3 minus 2s is equal to negative 3 plus 4s, right? And then I got 6 is equal to 6s, s is equal to 1, and t is equal to 2s minus 1, so t is equal to 1. And so these lines are intersect when s is 1 and t is equal to 1. Okay. And then let's plug this back into either one of them because s is 1 and t is 1. So L1 evaluated at t equals 1 is going to be 3 plus 2 is 5. Negative 1 plus 4 is 3. 2 minus 1 is 1. All right. And we'll just make sure of this. So L2 at s equals 1. You got 1 plus 4 is 5. 1 plus 2 is 3. Negative 3 plus 4 is 1. And yeah, so these guys are going to intersect then. So this is the point of intersection 531. Okay, cool. Nothing too hard. Just I think this is algebra 2 in high school. Solve systems equations quickly. Got it? All right. Now let's get one step more. So now we intersect a line and a plane. Okay, and what happens here? So now I need to dig for a problem that we can actually do. Let's see, intersecting lines and planes. Okay, got it. So let's do then. Oh, and this one was 12.5.61. We're actually going to be returning this problem soon because there's actually this 12.5.61 is a multi-part problem. Okay, so now let's look at 12.5.54, and What do I have? Well, let's look at 56 instead. So I got a line, which is x is equal to negative 1 plus 3t, y is equal to negative 2. Let's do 55. X is equal to 1 plus 2t, y is equal to 1 plus 5t, and z is equal to 3t. And then you got a plane pi, which is equal to x plus y plus z is equal to 2. All right. So this is what we have, and I want to see where they intersect. Well, if we think about it, right, you got a plane, and you got this line running through space that's going to run into this plane, right, and touch the plane. So, but what is true about being on the plane, right? When you're on a point in the plane, you're going to satisfy the plane equation, right? Because all points in the plane satisfy the plane equation. So that means when this line intersects the plane, the line has to satisfy the plane equation. So that means all we have to do is then plug in x, y, and z for x, y, and z. All right, and then we solve for t. So very simple. So in this case, we got 1 plus 2t, and then plus 1 plus 5t plus 3t is equal to 2. Right, so this is what x, y, and z are. I'm meant to have a different color here, so that would be x, y, and z. Okay, and again, that's because my plane equation is just x plus y plus z equals 2. If I had like random shit out here like 4, negative 3, 7, 11, right, I'd have to multiply these guys by the coefficients. So this then would have to be multiplied by whatever. This has to be multiplied by whatever. You guys get the idea. Okay, so you just plug in x, y, z into the plane equation, and this is equal to 2. So now I've got to solve for t. This becomes 2 plus 10t is equal to 2. Okay, and it looks like t is equal to 2/5. Alrighty, and now what? So, oh wait, I'm dumb. T is equal to 0. Okay, subtract 2 from both sides. 10t is equal to 0, and t is equal to 0. Whoops. Okay, and so t is equal to 0, which means my line intersects the plane at t equals 0. So now I got to plug in t equals 0 back to my line equation. So we got to evaluate the line at t equals 0 is going to be, well, that's just 1, 1, 0, right? 1, 1, 0. And is the point 1, 1, 0 on the plane? Well, yeah, because x is 1, y is 1, z is 0. So that adds up to be 2. And yeah, so we see that the intersection then of the line and the plane is going to be at t equals 0. Cool. Okay. Any problems with that? Shouldn't be. Pretty straightforward for lines and planes. Okay, now, intersecting planes. This one's pretty interesting. So let's attempt a shitty drawing here. I'm really bad at drawing. So let's say I got that guy, and then let's say I got this plane. Oh, God. All right, so yeah, so let's say these two planes intersect at that line right there, okay? So what are we going to notice? Well, for this plane, right, that continues through, and then we see over here that this guy will continue through, and then like that, right? So at this point in time, this blue plane is going to have a normal that looks something like that, okay? And then this purple is going to have a normal that looks something like that, right? And then they intersect at this line. Let's make it green right here. That runs through like that. So you got your normal and you got your intersecting lines. What's going to be true? All right, so here's that normal to the blue line, okay? So what's going to be true about this line that is the line of intersection, right? Well, I didn't draw this very well, but these normals are going to be perpendicular to the green line, the line of intersection, right? This is the intersecting line. And then this is going to be normal of 1, and then or normal plane 1. So let's call this pi 1. And then this is going to be the normal of pi 2. Okay? The intersecting line is going to be perpendicular to both n1 and n2. So what does that mean? That means that the intersecting line, okay, is actually going to be the cross product of n1 and n2, or the vector part, right? So remember, lines have a vector equation times t, and then you add a point, right? Again, from the equation of a line. There's a vector component and a point. And so what we have to do then is we need to find n1 and n2, right? And then we need to cross product them to get the vector part, all right? Then we need to find a point where the two planes intersect. So we need the vector part of the line of intersection, right? And then we need the vector part, and then we need a point on the line. Cool. So provided the two planes don't run into each other, provided that 2 points do run into each other, this is what happens. Again, you can have parallel planes. We're not going to discuss that right now. Okay. So let's take a look then at this equation. Not equation, but what example should I do? Are they just not going to have intersecting planes? Oh yeah, cool. Okay, so let's do 58. So 12, 5, 58. All right. So pi 1 is going to be this plane. It's going to be the plane 3x minus 6y minus 2z is equal to 3, and then pi 2 is going to be this other plane, 2x plus y minus 2z is equal to 2. Okay. So again, we need two things. We need a vector and we need a point on the line of intersection. All right. So the vector part's easy, right? So the vector is going to be n1 cross n2, which is going to be equal to, so I, j, k, and by this point you should be really comfortable with your normals. 3, negative 6, negative 2, 2, 1, negative 2. Okay, and so this is going to be I, negative 6, negative 2, 1, negative 2, minus j, 3, negative 2, 2, negative 2, and k, 3, negative 6, 2, 1. Okay, and then this is then negative 12 plus 2, so negative 10i. All right, minus, that's negative 6, that's plus 4, minus, so this becomes plus 2j, and then this last one, 3 plus 12, plus 15k. All right, so this is my line. The vector part, v, is going to be negative 10 to 15. All right, now, what do we need? Now we need, did I do this wrong? Did I copy this wrong? Oh, damn it. Yeah, that's positive. Okay, so this is going to be a positive 14. All right, so 12 plus 2. Okay, it's 14. Good. Got it. We're good. All right, so this is going to be my vector component of the line. And so now we need a point on the line. But if it's on the line of intersection, right? If the point is on the line of intersection, say this red point right here, it's going to be on both planes simultaneously, right? Does that make sense? So I need to find a point that satisfies both planes simultaneously. So I need a point that satisfies both plane equations. How do I do that, right? I got 3x minus 6y minus 2z is equal to 3. I got 2x plus y minus 2z is equal to 2. So how am I going to satisfy both plane equations when I have 3 variables but 2 unknowns, right? I have I have 2 equations, 3 unknowns. These are my 3 unknowns, and I've got 2 equations. Well, here might be something that doesn't sit well with you. It's okay. We're going to cheat a little bit. So let's think about this. This line right here, okay? This line right here extends on forever, for infinity. This green line is going to extend on for infinity. This vector component tells us that, okay, it's moving in a non-trivial direction, right? It's not going to be parallel to any of these axes. So that means at some point in time, this green line will run through a point where z is equal to 0. Does that make sense? So at some point in time, because this line extends for forever, right? And it's not parallel to the z-axis because of this vector equation telling me that, right? It's moving in a z direction. The z direction is not 0. Then at some point in time, I am going to run into a point. Let's say here's my z equals 0 plane right here. This line is going to breach z equals 0 as well, okay? So this, at some point, this line will hit something z equals 0, okay? Cool, got it? So what does that mean? That means that then this line, remember, this line is the intersection of both planes, except that, you know, this I didn't draw both planes. These planes technically do extend out forever, right? So this green line is going to extend out forever as well. Okay, so at some point, we're going to have z equals 0. So let z equals 0. You can let y equals 0. You can let x equals 0, right? As long as these guys aren't 0, then you have to be very careful. And then what do you get? So now I have 3x plus 6y minus 4 is equal to 3. And I got 2x plus y minus 4 is equal to 2. All right, so now I got two equations and two unknowns. We can solve this. So what do I get? This is 3x plus 6y is equal to 7. 2x plus y is equal to 6. So it looks like y is equal to 6 minus 2x from this last equation. And then we plug that into here. 3x plus 6 times 6 minus 2x is equal to 7. 3x plus 36 minus 12x is equal to 7. Okay. This, boy. This doesn't seem too nice, does it? Did I do anything wrong? Y is equal to 6 minus 2x. It's true. So y is equal to 6 minus 2x. 36 minus 12x. Okay, anyways, you get 9. You get negative 9x is equal to negative 29. And x is equal to 29 over 9. And so y is going to be equal to, what is this? 6 minus 29 over 9. 6 minus 2 times 29 over 9. And that's equal to 6 minus 58 ninths, which is equal to negative 4 ninths. Okay, so we got this point, 29 ninths, negative 4 ninths, and 0. Right, so that's going to be a point of intersection. And is that even true? What? That does not seem right at all. Let's see. Let's see where I went wrong here. So you got minus 2z. Oh, z equals 0. What am I doing? Z equals 0. I don't know what. Okay. Okay. Whee! All right, I don't want to redo this video, so you guys have to live with this mistake. Sorry about that. Again, even I, who has done this multiple times now, will make mistakes in a recording. Z equals 0, so these guys just drop out. There's nothing here, right? If you plug in 0 for z, and so now what? So now I get y is equal to 2 minus 2x, and so I get 3x plus 6 times 2 minus 2x is equal to 3. 3x plus 12 minus 12x is equal to 3. And at negative 9x is equal to negative 9. X is equal to 1. All right, good. Makes more sense. So x is equal to 1. Y is equal to 2 minus 2x. So y is equal to 2 minus 2 times 1, since x is 1. and that means y is equal to 0. And so now I have my point is 1, 0, 0. Okay? Does that make sense? So these points, these planes, right? I have two planes. I need to find the vector equation, which comes from the normal, and then I need to find a point that satisfies both plane equations. Since this vector will travel in a non-trivial z direction, it's not parallel to the z-axis, that means it'll intersect the z-axis at some point, or intersect the z equals 0 plane at some point, which means that at some point in time, this line is going to be at some point that includes 0 in it for z. And then because of that, I'll let z equal 0. It disappears in my system of equations. So now I'm left with two variables of two unknowns. I can solve this system of equations of two variables and two unknowns, and I get my point, which is 1, 0, 0. So finally, then the line of intersection is going to be the point 1, 0, 0 plus t times the vector 14, 2, 15, which is what we got from above, right? 14, 2, 15. Okay, so that's how you find intersecting lines, intersecting points and lines, and intersecting planes, which is definitely the hardest out of all of them. As you can see, lots of places where it can go wrong. I'm glad I caught my mistake in this video so I didn't have to redo it. All right, so that's that. And in the next video then, I'm not sure if we're on to skew stuff or like parallel stuff. Let's see what we're on to. Distance between skew lines and parallel planes. Okay, so here we talked about intersection. The next time we're going to talk about those cases I mentioned where what if two lines are running parallel, or if they're running skew, or what if two planes are running skew from each other, and we'll talk about how to find distances in those cases.